Thank you so much. Well, thank you for having me. And I've already realized that my title is way too long, and we've learned from this to never have titles above 5 words. Um, but basically, I'm going to be talking about a paper that came out a couple months ago that we worked on together with Alex Bellin, Susanna Bintania, and Alejandro Castro. And, it's going to talk about thermal CFTs, of course. But as a very specific type of CFTs, in particular, the question I want to start with is what is a holographic CFT? Okay. So there's been a lot of work on it, and when I'm speaking of a holographic CFT, what I really mean is a CFT that on the bulk ADS dual is dual to weakly coupled Einstein gravity. So, we can have different definitions, but this is my definition for a CFT. And there's certain things that we know that in some sense must be true or that we expect to be true from a CFT that we call holographic. In particular, for example, we expect it to have a large central charge because the central charge is related to the Newton's constant. And so if we want weakly coupled gravity, we need a small gn. On top of that, we need to be able to distinguish multi and single particle states, and usually we get this from some kind of large N factorization. And this is not going to be a full comprehensive list, but these are some main ones. Another thing that we want is a large gap. In other words, we don't want any kind of higher spin currents at low dimensions. And then the last one, this is from HKS, and we'll be working in two-dimensional CFTs, is we want a sparse spectrum. And with sparse, HKS tells us that we shouldn't really have any growth of states above Haagen-Dazs for large dimensions. And what this gives us is this will enable the CFT then to have a Hawking page transition. So these are some points that we, mostly agree on should be attributes of a holographic CFT. But what is really missing is that we don't have a full necessary and sufficient condition list. So, these are conditions that we think must hold true, but there might be others that we really need, or we definitely are missing some. And in particular, we also don't really understand, are these some of these conditions, do they follow from other ones that we've already named? In particular, what I would really like to have, in some sense, is a smoking gun. So I would like to look at a CFT and be like, yes, this CFT, if I calculate X, Y, or Z, this thing tells me it's going to be holographic or it's definitely not holographic. Okay. So recently, there's been some work with phenomena algebras, and there's been some very interesting conjectures about them, and specifically about this topic. So in general, I'm not going to give a very long discussion about phenomena algebras because mostly I don't feel qualified to do so, but also because we won't really need any of the specific details. But in general, these phenomena algebras basically classify operator algebras, and in some sense, it splits them up into different types depending on whether you can what a density matrix is well defined or traces are well defined. So for example, we'd have something like type 1, where you have the Hilbert space factorizes. And we have very well-defined traces. Then there's something known as type 2. And we'll never need these types again. I'm just giving you a flavor of what this looks like. In this case, we don't have any factorization of the Hilbert space. But in some sense, you can renormalize the trace in order for it to become well-defined again. And type 3, and in this case, you can't define a trace. It is impossible. There's no trace. in that sense. And type 3 in some is the usual QFT scenario, whereas type 1 is more of a quantum mechanics scenario. But if you want some examples attached to it, this would be, for example, if you had n equals 4 super Young-Mills at finite, strictly finite n, whereas type 3 is what you'd get if you take n equals 4 super Young-Mills and take the n goes to infinity limit, and lambda is not equal to 0. Okay, so these are some examples. And so why am I interested in this? Well, there's been some very interesting work by Sam Leuthäuser.
Sorry, may I ask a question?
Yes.
So, is it clear that, so at finite n, I agree there is a trace which is well defined, the Hilbert space factorization, all these things I understand. But at large n, you say there is no trace, no concept of trace, right? So is it
Yeah,
clear
so
that
in
there
some
is no
sense,
trace?
it's that the density matrix, I mean, the important part is the density matrices. And these matrices can't just, there's no universal one in that sense. So that's how tight, I mean, it's a very abstract concept, I think, but yes.
But if it is well defined at finite n, what happens if you take the limit from there?
Um, in the limit, you basically, how does this work? I think basically in the limit, because once you take infinite n, you have, way too many degrees of freedom. And
Mm-hmm.
this will basically mean that one could hope in some sense that in type 2, again, you have these infinite dimensions of freedom, but there's certain ways to renormalize this
I see.
where you're only interested in differences, whereas in the type 3 case, this is not true anymore. This is not possible.
Okay, thank you.
Anyway, yeah, so there's been some very interesting work by Sam Leuthäuser and Hung Lu, as well as following up on that, Elliot Gusteau and Hung Lu. And they've basically connected these von Neumann algebras to basically bulk features, and then use these bulk features to give some information on the boundary side of CFT. So in particular, they were looking at n equals 4 super Young-Mills at infinite n. So these are very strict infinite n statements. Everything in this talk as of this point will be n goes to infinity. We won't be looking at finite n at any point. And they found that basically below the Hawking page temperature, you have a spectral density that is discrete. So this is our spectral density. And the spectral density you can basically extract from the thermal two-point function, and this is where thermal comes in. And you have a discrete spectrum, whereas at temperatures higher than the Hawking page transition, you have a continuous one. So it looks, very roughly sketched, something like this. And their conjecture is that, in this scenario, you have the theory is dual to a black hole, whereas in this case, it is not. And so the conjecture basically is that if you have some kind of emergent spacetime, if the two-point function has a continuous spectral density. Emergent spacetime, or in some sense, a horizon structure. Okay, so that kind of brings us back to this original point. So in some sense, this is a proposal of some kind of smoking gun, where if you look at the spectral density of a CFT or the two-point function, and the thermal two-point function has this continuous spectral density, their conjectures that this will mean that there's some kind of space-time structure or dual space-time. And so what I would like to do today is look at this conjecture in a very specific example that is not n equals 4 super Young-Mills.
Sorry, small question. I think I'm being slow. You were saying that Hong Liu and the two other collaborators were connecting to von Neumann algebras, but it can
Yes.
only be type 3, right? Or there is refinements within type 3.
There are refinements within type 3.
And that's what they do.
Yeah, so they're basically looking at the fact that, you can so basically you look at subalgebra, so you take subregions and you kind of classify
Uh-huh.
the algebra within this region, and depending on what kind of algebra you have, it'll have some kind of effect on the thermal two-point function. So they were able to prove one direction for
Subregions in
sure.
the CFT, and then the
Sorry, what was the first thing you said?
subregions in gravity or in the CFT?
So you would look at so the way they were looking at it is they were looking at everything's argued in some sense from the bulk to start within the bulk, where they've, looked at, they're starting off usually with a thermal field double state, and then they look at some kind of subregion on the boundary and how this is related to a causal diamond in the bulk, and whether or not this causal diamond has all the information that is necessary to kind of reconstruct to go forward. And that'll tell you whether or not the algebra is complete or is the full algebra of the CFT, or if it's just a sub algebra thereof. And basically they relate whether or not it's a subalgebra or the full algebra to the type of von Neumann algebra, and therefore then the spectral density. And then basically they pull these conclusions and say, okay, let's ignore this bulk, even though it's coming from the bulk, let's make this a purely CFT statement. And so then they can, if you're going from the bulk from like a black hole, you'll definitely have a continuous spectral density, mostly just also you can see this because, there'll be a decaying 4-point function, there's a lot of chaos and stuff like that in a black hole. And so their conjecture in some sense in the other direction. Can we define this bulk structure, some kind of horizon, from just a purely CFT calculation?
I see.
Okay. So I said I wanted to do this in not n equals 4 sigma models, and in particular I want to do it in a 2D CFT. So the setting I want to do this are in symmetric product overflows. Oh my God. Okay. So I'm not expecting everybody to know how symmetric product overfolds work, but basically what you're going to do is take your favorite compact 2D CFT. Mine is going to be the Ising model, but you can choose anything. It can be a nonlinear sigma model. It can be any kind of minimal model. And you take this n times. Okay, so you take this seed CFT and you take a total of n times. And so you have n copies of this, and then you're going to gauge out by the symmetric group. Okay, so in some sense, you can think about it as you have each copy of the CFT a bunch of times, and you gauge out by the symmetric group. Okay, so why is this interesting? Well, symmetric product overfolds have some gravity-like features. In particular, as we mentioned kind of earlier, they have a large central charge once you take the number of copies of this original seed CFT large, because the central charge is related to the seed CFT times n. And so take n large and you'll immediately get a large central charge. And then because of this modding out by the symmetric group, you have a way of having a large n expansion. So this large n factorization comes basically from combinatorics. And so again, you'll have single and multi-particle trace states, multi-trace states. And on top of that, you can show that, and this holds for every symmetric product overfold, irrespective of what seed you're looking at, is you'll have a sparse spectrum. So it satisfies HKS, and what does that mean? It basically means that the thermal partition function will look exactly like that of 3D gravity. So those are great points, but symmetric product orbifolds are not dual to Einstein gravity. And why is the case? Well, one of them is that they have an infinite number of higher spin currents. So, the easy way to do is that every one of these theories will have a stress tensor in this, and you can basically use the stress tensor to construct any number higher spin also current out of this by placing it on different copies of these seeds. And so therefore you have an infinite number of these. On top of that, it does have a sparse spectrum, so it satisfies HKS, but only just barely. So you have a Hagedorn growth of states. And so spectral density goes as 2 pi delta. And where are these states coming from? Well, you have the original operators from the seed CFT, but you now have a new class of operator, which are basically twist operators. So basically, the easiest is you can choose like the identity, and instead of going back to just staying within the copy, a possibility is that you can have, you can basically, once you go around a circle, you can go from one copy to another one and then go back. So this Hagedorn's growth of states is coming from the fact that you have very large twist operators the moment you take and going large, and you can have basically operators that span many, many, many copies. And this is where this growth of states is coming from. And on top of that, you can show that these are the symmetric product orbifolds are not chaotic. In other words, the out-of-time order correlator doesn't decay. So you can show this. And therefore, it's really not dual to Einstein gravity. Okay, so I'm not saying it's not very interesting to look at because, again, it has those first 3 characteristics that make it look like gravity. So you can study it. You could study marginal deformations of symmetric product orbifolds, etc. But it itself will not be dual to Einstein gravity, and that's our key point for today, for now. Okay, and there's very known duals for string theory duals. So, for example, if you take a nonlinear sigma model on T4 or K3, you'll get a tensionless strings dual in ADS3. So there's very specific examples one could work with. But today, my goal is to basically first look at correlators, in particular thermal correlators, in symmetric product orbifolds that are universal. In other words, that the correlator is the same irrespective of what your seed CFT is. So I don't care, for example, about OP. For example, I don't want information of, for example, 3-point functions within these seed CFTs.
Sorry.
Yes.
Does this characterization holds also for cyclic orbifolds, where you gauge out the Zn instead of Sn?
Yeah, so certain parts of the results that I'm going to mention will also, so you can equally do this. Certain results, and I can point it out, will hold for like Zn, for example. What will be very important is to whether or not they have these long twisted states.
Okay, so
if you take, for example, Z2 to the n or something like that and mod out by that, that's not going to have lots of long twisted states, and that's immediately going to, none of these results then would hold.
Okay, thanks.
I will, at every point of the talk, only be talking about symmetric products, but the thermal 2-point function that I'll be looking at, you can generalize this whole thing easily for other, permutation groups, for example. Okay, so I said I want to find universal correlators, and the easiest part to start is 2-point functions. So I would like to look at thermal 2-point functions in a generic symmetric product orbifold theory. And I'm going to do this by using a method of first finding the partition function that was developed by Bante. Bante. And then I'm going to modify it to basically add insertions of operators to get a 2-point function out of it. But I'm going to first very quickly review the thermal partition function. So the partition function of a SN orbifold is going to be given as follows, and this is for fixed n, and at the end we will take n to infinity. So you modify the size of the group, and there will be a sum and a product. And so what's going to happen is, remember we had all these copies of these seed CFTs, and in order to find the partition function, we will need to sum over all the different covering surfaces. And sorry, I should have mentioned, we'll be doing this on a torus at first. And we can parameterize these covering surfaces basically by G and H. Sorry, but basically, so G and H are going to parameterize all the different covering surfaces. G is, in some sense, you can think of one cycle of the torus, and H the other cycle of the torus. And so for example, if you take G as just a single cycle, then H will be the whole symmetric product group, and therefore you'll just get the untwisted sector partition function. But in general, you can think of, in some sense, like, let's say G equals a cycle of length 2, it's basically telling us that we have one of these copies and we're gluing another part of these copies to it. And, the covering surface of a torus gives you another torus. So it's just a bigger torus. So these G's and H will tell us basically all the different ways of gluing all these tori together, possibly in disconnected pieces. Yeah, so this is the untwisted sector. Yeah, and then the product here is we're going to look at, let's say we've chosen a G and an H, then we're going to look at all the different connected pieces, and each of these connected pieces is basically parameterized by an orbit of G and H. And we'll label this by xi. And for each connected piece, we'll have a seed partition function dependent on the connected modular parameter. So the modular parameter of a single torus for a single seed will be tau, and since you might have some larger torus of the covering surface, the modular parameter changes, and I'll explain how exactly in a second. Are there any questions on this point? Because we'll get back to this many times. So this is the part where it'd be very interesting.
Yeah, maybe
so
just
for
a small
example,
question.
yes.
Yeah, do you always obtain a torus in a sense that, for example, if you have a twist in a given compact direction, I see that you always get a torus. But if you simultaneously twist 2 directions, is it obvious that it's a larger torus in both directions?
Is obvious. I can't think of like a very specific example where it might not be obvious, but it's definitely the case that you will always get a torus. So for example, you'd end up with something like this and then this, but then you could also continue on here, for example. So in this case, you'd have basically G is some cycle of length 2, and then H would also be some cycle of length 2, probably squared. But yeah, you'll always as long as you're staying with no actual twisted insertions, you'll always stay with the torus.
Okay. Thank you.
Oops. Okay, so basically, again, G and H will basically tell you all the different covering surfaces, and Xi will basically label all the different connected components that you have with a certain G and H. And so one thing you can look at, so I just kind of already said this, but if you take G to just be single cycles for everything, then H will just be summing over the whole symmetric group. So basically, you can think of H as the role of H is basically just symmetrizing everything. And it's not as, I mean, it won't be as clear once you take a non-trivial G that H does the same, but that we can think of in some, that's what we should keep in mind, is that G kind of like labels what the different sectors are, either untwisted or different twist sectors, whereas H is kind of really just symmetrizing over everything. Okay. And I said, like I said, for connected cover, the torus will be bigger. So this parameter xi will depend on different parameters. I'm going to just give you the exact definition. Oops. And this will depend on the G's and this H that are chosen. But in particular, I want to point out this part, which is the most important part, and it basically tells you if you have a certain, or if you're looking at a certain connected component, what is the length of G in this connected component. So this is the most important parameter for our purposes, hence why I'm highlighting it. And the other ones, they kind of depend on, for example, the relation between G and H, as well as the number of G orbits and stuff like that. But this lambda is the parameter that we'll be really looking at today. Okay. So this was Bante's formula on how to get the partition function. And at this
Sorry,
point,
can I just
yes.
ask about this lambda? What is this lambda precisely? How do you compute it? It's fixed for a given choice of n.
Yeah, so
and once you fix G,
in my very similar simple setup where I had my two I shouldn't stop erasing, I think. This lambda would just be 2.
okay,
So it kind of just
it should
tells you
take
what the
care.
length of G is in one direction. I think this is telling
Okay.
you lambda.
Okay.
How many copies is it kind of spanning over? I think. And in some sense, it'll tell you just basically how big is this torus getting in a certain direction. Okay, so and because this comment came earlier, this Bante's formula is not technically only for Sn. So you could have used any permutation orbifold in this case. I'm going to only be writing equations for Sn just so that it doesn't get, too overwhelming. But you could use this, and it's very nice to use for any other kind of permutation orbifold. Okay, so like I said, I don't actually want to be looking at a partition function. I would like to look at a 2-point function. And so what I'm going to do is basically I'm going to insert operators into this partition function at certain points. And I'm going to start with, let's say we've inserted n operators onto one of these connected pieces xi. So you'll get an endpoint function, and we'll generalize to 2 and 1. But I'll write them on some connected point component psi. And I'll define it to take the following form. And so I've inserted operators on the different copies. So once you insert an operator on a copy, it's the seed operator. So it's some operator from the original seed CFT. And S is what I'm going to write for seed, just so that you remember. And this is going to be equal to give myself okay, so we'll have the operator inserted on one of the copies, but we have to account for the fact that we have that this torus needs to have, we need to account for the periodicity of the torus. So, you can, if you have a connected component, or if you have multiple copies of the seed CFT that are now connected, you'll be inserting on one, but it also has to periodically be inserted on the second copy and all the other copies that have been connected to this one connected component. And so we have to sum over these different pieces. So I'm just going to write it down, and then we can look through it. So basically what I'm doing here is that I'm inserting these operators on some connected component, and with modular parameter of this connected component. So then this is where this lambda is coming from. This is just the Jacobian factor. This is why I'm kind of highlighting it. And then these sums are coming from all the different directions, the two different directions that you can insert this copy, because these are all the different copies that I can insert my operators. So for example, again, my two-piece thing, I kind of have to sum over the fact that I can either insert it, let's say right here, or I could insert it in the periodic part there. And I would be summing over all the different insertions that I can possibly have. Okay. So so this is how I'm going to define this G, basically. So think it's not a full correlator, but it's in some sense the correlator on one of these connected components of the covering surface. Okay. So then let's continue on to the two-point function. Okay, so I'm going to write down the whole part, and then we can break it down. So these are the two-point function of the full operator of the symmetric approach orbifold on the torus. So the n is coming from the normalization of the operators. Sn is from the original equation that we had. And so we're going to have two different contributions. We can have a contribution coming from a connected term, basically where we've inserted the two operators on the same connected piece. And this will give us this two-point function that I just introduced above. And all the pieces that are not connected to this piece where the operators are insertions, we'll just have our seed partition function. But then there's a second component where I could have taken these two operators and put them on different connected pieces. And then they can't really speak to each other. And so you'll get two one-point functions. And again, all the other components will just get other copies of the partition function. Okay, so this is a general two-point function. And at this point, again, technically, this works for any n. This works for permutation orbifolds. Yes. One thing I'm not going to do is I'm not going to show that this, you can show from this when we do in the paper, but I won't do it for today because it's incredibly boring. You can show that this will reduce down to the expected singularity if you take the two operators to go together. But one thing I do want to comment on is that this is not, so these two parts are not exactly equal to the connected and disconnected piece of the two-point function. The reason being that, so I mean, this definitely is a part of the disconnected piece, but you could still have a disconnected piece to the two-point function of the seed operators in this part. So there's a small part of the disconnected piece still in this connected part of the orbifold of this, correlator. So just making a note of that. Okay, so we have a correlator, and now what I'd like to do is take large N, and in particular, I'll take tau to go as I beta, and therefore a high temperature as well. Okay, so I'm going to use a certain fact first that I won't show, but you can show this from the partition function equation from Bantai's formula that I discussed. But at large temperature or high temperature, so in other words, beta smaller than 2 pi, I'll be using the fact that the leading contribution to the sum over these covering surfaces comes from these long twist cycles. So, this is in some sense connected to the fact that I mentioned earlier that this Hagen-Dörn growth of states that you get is also coming from long twisted operators and stuff like that. And like I said, you can show that in at high temperatures, the long twist cycles are the ones that dominate. And so the assumption we're going to do is that if we're taking light operators as probes, that they won't change the dominating contribution thing. And so this is similar in some sense as if you take, for example, a path integral and you're looking at saddle contributions. If you take a probe of the saddle, the probe is not going to change what is the dominating saddle. Okay, so I'm going to take a simple case. Okay, I'm going to first take a very specific covering map, and then we can see what happens, and then we can argue how it will look like in generality. In particular, I'm going to take G to have the form of a bunch of single cycle parts and one long cycle. And then H is just going to take a single cycle so that it commutes with it. In particular, so this L is a very long cycle, the ones that dominate, and L is going to go roughly as N. Okay, so a covering map of this type is definitely a part of the sum. So basically what we're saying is that we have one contribution of lots and lots and lots and lots of toruses, and everything else is left over as single copies. And so there's an L number of these. And of these, there's N minus L of these. Okay, so we have in total N minus L plus 1 connected components. And we have one component that has length L, and therefore that has this tau psi equals tau over L. And then we have N minus L components have a very similar tau, where tau psi is just equal to tau. Okay, so let's look at this very specific case and look at what these two contributions do, and we'll start with this 1-point function part here. In particular, in this limit, so for the 1-point function, we can again have two different contributions, okay? We'll have one contribution or we'll have N minus L contributions where we have inserted the operator on one of these pieces, so one of these single copies, and that contribution will go as follows. And then we'll get a second contribution where we've inserted this one operator on the long cycle, and that will look like this. Okay, so what I'd like to do is I'm going to take L to scale basically with N and to be very close to N, and therefore this contribution is going to fall away. And what you might think is that you might be worried that this contribution is going to grow very quickly. But I want to make note here of this effective temperature now. So if I take tau goes as I beta, then this 1-point function of the seed operator is going to fall away exponentially. And so this contribution is going to vanish as well. So this one goes away too. So in general, so these two parts, you can do the same analysis. So both of these will go to 0, and we'll kind of only be left with this. And now I'm going to do the exact same analysis to this part. Okay, so now I'm going to look at the 2-point function part, or the connected component part. So again, for the connected component, we can have two different contributions. We have one contribution where we've inserted the two operators on this one large long cycle, and that contribution will look like this. So this L is coming from the Jacobian again, and these are the two seed operators inserted on this giant torus now. Okay. And then the other contribution is again where the two operators now get inserted on the same connected component, but this connected component will be one of these single cycle components, of which we have n minus L of them. So n minus L. So the same reasoning is going to happen as is going to go through as before. This n minus L is going to go to 0. So this component falls away, and we're only left with a single component. Okay, so we're really everything boils down to this one component. And where is this coming from? Again, there's these two operators that we've inserted on the long twist cycle. Okay, so what is important here? Well, we know what the thermal two-point function looks like at infinite temperature. And because we're taking L to go to infinity, the temperature on this gets basically enhanced. And so as long as L goes to infinity, we can use the thermal two-point function result of the seed CFT. And that'll look like this. So then we can insert, so we can take, that's here. And so for beta goes to 0, we have this result. And this is all to the power of 2h, sorry. I'm writing significantly larger than I usually do as per usual. There's probably no space. But we can insert this two-point function into here. And what I want to comment on is this will hold even if the original temperature of the symmetric product orbifold that we're looking at is finite or is high, but not infinite. Exactly, because we have these long cycles that go to infinity that will enhance the temperature, making this a very valid replacement that we can make. Okay, so we can insert this into here, and I'm going to massage the whole thing. So as long as L goes as n is a lot larger than 1, this contribution is going to take the following form. Okay, plus any kind of like 1 over n corrections. Okay. So, like I said, I want to stress that this holds for beta as long as beta is smaller than 2 pi, but it doesn't hold but it doesn't necessarily need beta to be around zeros, I think, because this enhancement of the temperature. So basically what's happened is twofold. The long twists that dominate the partition function have done two things for us. For one is that they've increased this effective temperature. But then the other part is that they've given us now this sum over images thing. And I'll massage this very soon into a very nice form. And then let's circle back. You might be saying, okay, fine. We've only looked at a single contribution at this point. But in reality, what we're missing is this sum over G and H. We've only looked at one component. And so my argument here is going to be as follows. The H we've argued already, basically the only role it really does is symmetrizing over the whole permutation group. And the long cycles will still dominate. And as long as you take a G that contains a long cycle or long cycles, you can always basically get an enhancement of the effective temperature, and therefore you'll be able to replace it with this, or replace the seed insertions with the thermal result at infinite temperature, and therefore you'll always get something of this form. Up to, possibly some numerical factors in the beginning to make, for the sum because you're summing over basically a bunch of these pieces. Okay. And so I'm going to rewrite this, or I've already written this actually very nicely, I think. I'm going to take a very special case. Let's say that we're going to look at a scalar, because in that case, we can resum this very nicely. So I'm going to rewrite the coordinates like this and take a scalar result, because then we can resum it. And for high temperatures, we get this result for the total thermal 2-point function. And what is this? Well, this is the same 2-point function that Maldacena found for scalar bulk boundary scalars propagating in a BTZ black hole. Okay, so this sum again being the method of image, being all the images of the BTZ black hole, and we can get the low temperature result by basically just taking, the S transform. Or in particular, we could also just take at low T, we could basically redo the whole analysis, but at low T, we'll find that the dominant contribution is coming from this states that will look like this, where L goes to infinity, and these are coming from the untwisted sectors. So G goes as 1, and H will now go as L. And so this is coming from the untwisted sector. And in this case, we have scalars in BTZ, whereas in this case we'd have scalars in a thermal ADS background. Okay. I'll stop there very quickly. Any questions so far?
Maybe to try to understand what the conclusion here is already at this stage. So is the fact that you obtain this expression really the conclusion that you find that you can associate a geometry, kind of a bulge geometry, to this CFT in the form of this BTZ black hole? Although it's only the information about the 2-point function?
So what I can the statement I can definitely make is that if you take, as long as they're light, if you take any seed operator, or single trace seed operator in a symmetric product orbifold, the thermal 2-point function will always look the same. So it's universal in that case, and you can relate it. It looks the same as if you had some kind of dual with the BTZ black hole. But if we kind of remember what I said in the beginning, we're not expecting, or we definitely know that the symmetric product orbifolds are not dual to just weakly coupled gravity, I think.
Yeah.
And let me make a couple more additional statements before I get back to the beginning. No. Just so that I can kind of hammer in. And then I'll get right back to what you said, and we can discuss exactly what we found. But yes, as I can say, the kind of summary result here is that if you take any light operator in a symmetric product orbifold, it'll have the following form. The thermal 2-point function will look like that of these operators in a BTZ black background, plus some 1/n corrections at high temperature. Okay, and I want to make a note that this method that we've done is only going to work for untwisted probes so far. So the problem is that the moment you want to add like a twisted probe, then these covering maps won't be the covering map of the torus won't be another torus again, and there you'll start having to include higher genus covering maps and stuff like that. So this method really is only going to work for untwisted probes. But I kind of talked in the beginning how I would like to find correlators in general that, or other correlators that are universal. And so one thing we did in this in our paper, and I won't go through the calculation because it's not as illuminating, I find. But you can also find 4-point functions, very special 4-point functions that again are universal for symmetric product orbifolds. And with universal, again, I mean they don't depend on any kind of like real data of the seed CFT. And what kind of 4-point functions can be universal? Well, once you calculate a 4-point function that has some kind of twist operators in it, again, you're going to have to go from this correlator to a covering map. And so on the covering map, if the correlator reduces down to a 2-point function, then this is going to, again, give us hope that it might be universal in general. And so we find that 4-point functions of the form, like here, have a very universal form. They take this, in some sense, this will hold for any n, but okay, so this result holds for any n. So this is basically, what is this? This is a 2-point function of some kind of probe operators again, now in a twisted background thing, and the twist is of some type of form n. And again, so what we can take is, let's take n large, and then the sum will go to infinity. And what is this going to give us? Well, at large n, you'll find that this twisted 2-point function is equal to, let me not rewrite this again, that of a massless BTZ black hole, again, plus 1 over n corrections. Okay, so this is a bit surprising. It definitely can't be massive because the dimension of these twist operators is less than that of the black hole threshold. But we're basically finding, and I want to make a caveat that we've checked this explicitly for twist 1, so in other words, untwisted, and twist 2, so the smallest non-trivial twist probes. But they have, again, a universal result that can be interpreted as some kind of states in some kind of like BTZ like black background. Okay, so now let me get back to Saskia's question. How can we interpret what I've just found? Well, we found that thermal 2-point functions and 2-point functions in twisted, thermal 2-point functions in twisted backgrounds take a universal form in symmetric product orbifolds once you take a large n limit. And on top of that, they look like fields in a BTZ black hole like background. And in particular, this is valid for any seed CFT. So this is not only for the very special results that we have, the special symmetric product orbifolds like the D1, D5 system. So this works for everything. And so if we kind of remember again in the beginning, there was this conjecture by Symm, Hong Liu, and Elliot Gastill that you could use these thermal 2-point functions to discern whether or not a CFT is holographic in some sense. And we're basically finding is that this is not going to work. You know, that's a very crude way of saying it, but you know, a symmetric product orbifold is not going to have a weakly coupled gravity dual. On the other hand, the thermal 2-point function will always look like this is that kind of thing. So it's always going to satisfy these the conditions of this conjecture. So it's definitely not a sufficient condition for holographic CFTs. But there's things that we can look at. We could look at 1 over n effects kind of thing, because those might resolve some of the ambiguities. And then one of the, we've been talking with Elliot and stuff like that. And so one of the possibilities is that because, symmetric product orbifolds are more dual to tensionless strings, there's the question as to whether or not, so there's these additional conjectures discussing basically what's called a causal depth parameter. And basically it's telling us that if you look at different probes, that they might have very different looking backgrounds that they can see in some sense different backgrounds. So one of the things one could hope is that in this case, if we were to calculate the causal depth parameters, that we'd find different ones for different probes, which is an indication, according to them, for a stringy bulk dual. So one thing I would like to note, though, on this section is that, as I said, we can't really look at, for example, untwisted probes in the two-point function mechanism that I was kind of describing. But in these thermal backgrounds, we don't find this. So far, at least for untwisted and for minimally twisted, so twist 2 fields, we find the exact same result, which gives us the same causal depth parameter. So, you'd have to work a bit harder to see how this plays in. Does that answer your question, Saskia?
I have 2 more questions.
Please.
To go back to like the work of Liu and his collaborators, like you were saying in the beginning that they kind of looked at the von Neumann algebra in kind of subregions. So is there a problem that they're precisely looking at subregions and not making some kind of like patching
No,
up
so
global?
the classification, so they start with subregions kind of thing, and then then they basically relate this information from the subregions, they use these subregions to kind of discern some kind of the differences in the bulk structure, I think, and then can use this to kind of look at the CFT part, but then they make, they basically kind of can then relate this information in the subregion to the spectral density, which is for the whole two-point function kind of thing. So they've kind of like, they have some very interesting mathematical proofs where they go from like one to the other. But basically they're saying that if this effect that they see using the subregions relates to the spectral density having a certain form, which is related, which you can extract from the thermal two-point function.
Yes. Okay. Okay, and then regarding to the last one that went a bit too quickly for me because most concepts I don't know, but is that somehow that you have kind of an observer instead, or in terms of probe dependent statement about whether you see something which looks holographic or not?
Okay, so yeah, so what the the differentiation between whether or not like the spectral density was just like continuous or discrete, I think this was originally the paper from Leuteza and Liu. And so that's a very kind of like crude kind of like statement. And so one or the other, it's either there exists a bulk dual or there doesn't exist a bulk dual depending on the spectral density. And so then the paper that followed up with Elliot Gusteau and Hung Liu kind of like refined this a bit, saying that basically that you can kind of come up with a new parameter that they're calling a causal depth parameter, and you can extract it from the spectral density. But the point being is that if you look at, for example, n equals 4 superioring moles at like finite but non-zero lambda, you'll find that this is dual to some very stringy geometry. And they find that dependent on what probe you're looking at, you get a different value for this causal depth parameter kind of thing. Whereas in the case where you take lambda to infinity, where you do have a dual that is weakly coupled gravity, in that case, the causal depth parameter is in some sense the same for everything, and every observer sees the same background kind of thing.
I see.
So in some sense, one of the possibilities of a resolution on our side would be that, you do see a BTZ black hole and nothing really else at the moment, for the probes that we've looked at. One could, in some sense, their argument is that you could look at, if you looked at other probes, you'd see kind of like a different background And that might give you that might kind of resolve the tension between the two works that we have, kind of thing. But definitely, if you want to only want to consider like a holographic CFT to be something that's dual to a weakly coupled gravity, this won't work. Like this discernment by spectral density, the behavior of the spectral density doesn't, is not enough to show this.
Okay, that's an interesting idea. I never thought about that. But I would have thought that somehow, like, if you had like just a fixed probe and you would know all its higher point functions, you would actually also maybe at some point realize that your background is not really BTZ. Is that something that can happen?
So yeah, so I mean, the moment you look at any of the higher point functions, it will 100% definitely depend on the seed CFT.
Yeah, okay, and okay, but you only want universal features. Yeah,
exactly.
Okay,
so
yes.
our in some sense our goal was to look at things that won't change depending on CFT kind of thing. So
okay, yeah.
I completely agree that once you have higher point functions or you add different types of insertions or something like that, then even in the 4-point function case, we've looked at a very specific twisted ground state, I think. Partially because, other ones are kind of hard to calculate, actually, because, you need to be able to invert the covering map and stuff like that. But, and it's, this is why we can't take this past, twist 1 and twist 2. One could guess maybe that the same holds for higher twist, but I have no proof of that whatsoever, nor can I really calculate this at all. Yeah.
Okay, perfect. Thank you.
Well, I don't have anything else past this. I've given my concluding remarks, I think, in response to Saskia's question.
Thank you,
but if there's any
Waltraut.
other questions, I'm happy to answer.
Yeah, we thank Waltraut for the very nice talk.